Mm-hmm. So I'd like to thank the organizers for the invitation and for setting up this nice workshop. So this is a work which is in collaboration with Hamid Afshar, Daniel Grumiller, and Hossein Yavartanu. So a part of this project has been already published, and a part of what I'm going to tell you today is coming out soon, hope in a couple of weeks. And so this is the outline of my talk. I'll give you a brief review to black hole thermodynamics and why do we really need black hole microstates. Sorry for being sort of boring for this review. Then I'll tell you about the residual symmetries, charges, and actually the need for refinement of equivalence principle. And then with this basic new picture that I give you here, I'll tell you how I can use that for describing black hole microstates. And for that, I need to tell you about the near horizon and asymptotic symmetries and the interplay between the two. And from there, I basically introduce the horizon fluff proposal. Okay. So as you all know, general relativity basically tells us that any coordinate system is associated with parametrization of the space-time and is associated with specific observer. And then equivalence principle is stating that physics should be independent of the observer or the coordinate system. And this is manifested in the GR through general covariance, which states that dynamical equations are basically covariant under general coordinate transformations, and the physical observables should be invariant under diffeomorphisms. And again, you know that in GR we have solutions which have horizon, which basically means that there are causally disconnected parts in the space-time, and horizons could be essential property of the space-time, like event horizons, or they could be observer-dependent, like Rinder horizon. And again, we know that black holes can form under standard GR dynamics. And again, about black holes, we know that we have several uniqueness theorems which are telling us with a given mild symmetry conditions and asymptotic behavior, the solutions to GR equations of motion are unique. So then there is another parallel description of black holes, which is basically black holes behave as thermodynamical systems. They have temperature, and there is a entropy associated with them proportional to the area. And the emerging picture for black holes are basically we have a thermodynamical system with Hawking radiates. Formation of black hole should be viewed as the thermalization process, and that thermalization process basically generates the entropy. But black holes also Hawking radiate and can eventually evaporate, and this process is not unitary. So this was just a very brief and a quick review of what we know about black holes. Then one of the very basic principles in physics is that physics at different scales are decoupled, which it implies, for this case, the case of physics of black holes, it implies that quantum gravity effects, which are presumably going to show up at Planck scale, should not be really relevant for description of the thermodynamic properties of black hole. So that's the viewpoint that I'm going to take, that we need not go all the way to a very deep quantum gravity level to describe thermodynamic properties of black holes. But on the other hand, we know that the GR, standard classical GR, as I just reviewed, by the fact that we have this uniqueness theorems, is not going to give us the black hole microstates. And we need to go beyond classical GR. But I just discussed that probably we need not go all the way to quantum gravity level. So basically the proposal I'm going to look for is to find the we should be able to find the microstates in some intermediate scale between standard classical GR and fully fledged quantum gravity. So and the idea that I'm going to use is basically we need to relax a little bit the standard strict statement of equivalence principle. And we already know that there are some well-known ways how to basically go beyond strict statement of equivalence principle. And basically the idea is that through many different examples that people have studied in the last 40 years or so, we know that there are certain diffeomorphisms to which we can associate conserved charges, and hence there could be some, or there are some diffeomorphic geometries which are not physically equivalent. So the very famous, the first examples of this kind was studied by BMS already 50, 60 years ago, and the next famous example was studied by Brown and Heno. So the general picture that this analysis have been is telling us is that probably this is a generic feature, that there are some diffeomorphic geometries which are physically distinct. And this already means that we need to a little bit refine the statement of equivalence principle. And the charges that actually distinguish these different diffeomorphic geometries are given by surface integrals, and generically they are non-local physical observables, not always generically, and hence this refinement of equivalence principle is not in contradiction with this strict statement of or the strongest version of the equivalence principle that I just discussed. So this is basically the viewpoint that I'm going to take, that there are many, actually usually infinitely many distinct geometries which are associated with the same black holes with the same mass and angular momentum and other classical charges. So, but the point is that so we have a big class of different geometries which are diffeomorphic to each other, diffeomorphic to the same black hole with the same mass and angular momentum. But the question is which of them is going to be relevant for the question of black hole microstates. And actually the simple answer to this question is coming from the fact that black holes do have a horizon, and there could be some geometries which are diffeomorphic at the near horizon level, but they are just the same when you are away from the horizon. And these are basically, I'll come into the more detailed description of them, the set of so-called near horizon soft hairs. And I'm going to basically give you a model how you can find black hole microstates through near horizon soft hairs. This should be distinguished from the so-called asymptotic soft hairs. So there are, when you have a black hole and when you have a horizon, there are two sets of these diffeomorphisms, which non-trivial diffeomorphisms, and those which would be relevant to the problem of black hole microstates are those which can be obtained near the horizon. Okay. So this is basically the general picture of the proposal that I'm going to formulate, at least for the simple case of ADS3 black holes. But presumably it could be more general. So the statement of the proposal, the rough statement, is that black hole microstates are labeled by the set of charges defined only on the horizon, which could not be distinguished by any observer at or away from the horizon. This could be generically an asymptotic observer. Okay, so let me just show you how this may work in a simple example of ADS3 black holes. So this is the simple Einstein ADS3 gravity. There are two parameters in this game, the Newton constant and the ADS3 radius. The very well-known black hole solutions to this theory are the BTZ black holes, which generically come with two parameters, r plus and r minus, and there are mass and angular momentum associated with these generic black holes. And to just review their thermodynamic properties, they have an entropy given by the area law in the first order, and temperature and horizon angular velocity and or left-right temperatures. Okay, so now just going back to the question of non-trivial diffeomorphisms and charges, the same theory has many different solutions, which are basically all locally ADS3, and I'm giving here a big family of them. A BTZ black hole is one of these, but in general here I have two independent functions, a plus and a minus, defined in this way, and there are functions of t and phi. If I impose Einstein equations on these general ansatz, this one forms A plus and A minus should be closed, and this is how I get this large family of black holes, or large family of locally ADS3 solutions. And I'm going to impose the condition that all these functions are periodic in phi, and I need to also solve for this equation. Depending on basically the properties that I want to choose on diffeomorphisms that would be relevant, the physically distinguishable diffeomorphisms, I can still impose some conditions on the solutions to this equation. And one relevant condition is taking the zeta plus and minus to be constant, and then j plus and minus would be a function of phi, two periodic functions of phi. And this choice would correspond to a canonical description of this set of solutions. And the reason why I call them canonical, because this choice would correspond to fixing the left and right temperatures at the horizon. So all sets of geometries which are given by these two conditions would be black holes of the same temperature at the horizon. And but this is the information at the horizon. If I want to translate it to the standard information of black holes at infinity, I need to relate the zero mode of this function phi to this zeta plus minus function in this way. Okay, so basically what I introduced was infinitely instead of infinitely many black hole solutions, all of them with the same temperature and with the same mass and angular momentum. Okay. Although here for black hole solutions, I take this J naught to be a real number. In principle, I can extend this J naught to be an imaginary number between 0 and 1 with this parameterization. And the imaginary case would correspond to conic spaces, conic deficits, and the global ADS. Okay. Another set of solutions is which I've called microcanonical description, is coming with a different boundary condition that I choose this zeta plus and minus to be equal to j plus minus, and the solution to dA equal to 0 is a generic function of t plus minus phi. So this is the most general solution in this class. Again, I have a class of infinitely many solutions. For real J naught, I'll have black holes, but in microcanonical description, in the sense that I have fixed the mass and angular momentum of the black hole instead of the temperature. So I gave you two general class of solutions. And if you want, there could be a map between the canonical and microcanonical descriptions. One of them I chose to describe with this function j. That was the canonical description. The other one, which was the microcanonical, I described by this function h. And they are related if I equate the energy momentum tensor for these two different descriptions in this way. So I'll use this later on when I want to describe the logarithmic corrections to entropy. So you may view this set of infinite set of solutions as a phase space, actually, in a very precise sense. There's a well-defined symplectic structure in this phase space, and with that you can define symplectic symmetries. These are basically directions on the phase space that keep the symplectic structure intact. And you can define brackets and conserve charges, the symplectic symmetries. So for the canonical description, actually these functions j define the conserved charges, and their bracket is which could be computed using standard, for example, covariant phase space method, or different methods that people have developed to be obtained in this way. So basically these two currents that these two j's, which were specifying the set of solutions that I had, would appear as conserved charges for this or symplectic charges for this class of solutions. And you can do a semi-classical quantization on these or their Fourier modes and get this simple harmonic oscillator algebra, where C is the Brown-Henno central charge. So this is a standard computation. Then from this, actually, one can construct Virasoro algebra. This is basically a Virasoro algebra at Brown-Henno central charge, and with this, and these J's are currents in this Virasoro algebra with this anomaly term. So this is basically, just to summarize, I have a set of solutions, all of them black hole solutions, if J naught is real valued, and there is this symplectic charges associated with them. Then you can basically try to construct the Hilbert space of unitary representations associated with charge algebra. And if you just note here, J0 is commuting with all the other generators because of this factor of n here, and hence the vacuum state is labeled by J naught, which is the eigenvalue of J naught, and these J n's are annihilation operators. Then you can construct the most general state in this Hilbert space just by the standard creation. Well, the basic algebra that I get, this is my symplectic symmetry algebra, is this. But I can, given this, I can construct a Virasoro algebra out of that. It's a U1 algebra, but if you ask what's the physical meaning of the Virasoro generator, at the level of geometry, this is okay. So there are different ways of saying this. The way I present it here is that I have a set of geometries, so you can replace this A plus and A minus by these J's eventually. And we have a phase space of solutions. And you can ask what are the transformations on this phase space which keep the symplectic structure intact. I didn't tell you the explicit construction of the symplectic structure, but it's standard machinery of, for example, covariant phase space method that could be used here. But the idea I want to convey is that you should view this as phase space, and you can call them asymptotic symmetries, but you can just a little bit generalize that and define all these charges everywhere you want. You need not be only defining them as in the asymptotic region. So I'm giving you a phase space of all these different solutions and asking what's the transformations on this phase space which keep the symplectic structure intact. And that those transformations are basically generated by variations in this J. J was the function which was defining any point at the phase space, or its quantum version, which is this. Okay, so any BTZ black hole in principle is related to state here in this phase space, as I have just written here. Then the rest of these states which come with excitations are Virasoro descendants of a BTZ black hole. Then there is another, so here if I take this J naught to be real, I am describing the sector of the Hilbert space associated with BTZ black hole, but J naught could be imaginary, and then with this convention of plus minus I over 2, I have the conic spaces, their Virasoro descendants, and global ADS3. So this was basically, but I should mention that all these descendants of a BTZ black hole are not a part of its microstates, because you can distinguish these charges if you are away from the horizon. And black hole microstates should not be distinguishable if you're away from the horizon. So we need to look elsewhere for black hole microstates. Okay, so and this elsewhere is coming now. If I start with this, just focusing on the cases where J naught is not real valued, this means that the corresponding operator is not Hermitian, and it's better to look for different representations or different realization of this the same charges or fields. And in particular, note that this J was not a primary field with respect to this Virasoro generators L. However, you can basically construct a primary field, which I've called W. And this primary field has weight 1, as one can just explicitly show from the transformation of this J. And but the point is that this field is not periodic. It has this twisted periodic behavior, and hence if you just you have a basically primary field of weight 1, and you can try to quantize it just proposing the standard commutation relations. Here I am just basically putting this by hand, but I'll justify it in a bit. So this is the algebra of the operators associated with the Fourier modes of these W fields. And if I assume that this nu, which was geometrically related to the conic deficit of this conic spaces, to be quantized in units of 1/c. So this is basically what I put by hand at this stage. Presumably this is what is coming out of a full quantum gravity description. For example, this is the case for D1, D5 system or other ADS3 geometries coming out of string theory. So in that context, this relation is what's called the spectral flow. But here I'm going to assume it, that's just put it by hand. Then I can gather all these W fields into a single J, where these J's are satisfying this simple algebra. So it's just a different way of relabeling them, but it's very well motivated why we need to do this. And the reason is that, let's suppose that you had a black hole and you're an observer sitting very close to the horizon, Rindler observer. And you may say, I want to repeat the same game that you did for BTZ black hole for this Rindler space, meaning that I want to find its non-trivial residual diffeomorphisms and associate charges with them. And the algebra that you would get is exactly this. So I could have obtained this algebra, which there is no sign of a central charge or anything related to the black hole, by just the same procedure that I described earlier. So this is the algebra of residual symmetries for any Rindler observer. Okay. You can construct a Virasoro algebra at central charge 1 out of these J generators, just the standard relation. But let's remember that these curly J's are the collection of all these W modes for various values of nu, the deficit angle. So let me summarize. What I had was the algebra of this straight J's, with here. J naught here could be real or imaginary. For the real case, I have the Hilbert space of BTZ black holes constructed out of this algebra. For the imaginary one, I have two different descriptions. One is basically given the states given here, and the other one is the states created by these W fields, and which eventually gathered all through this curly J, and the Hilbert space of this curly J's is going to describe the same set of all conic spaces. So I have two different descriptions for the same conic plus global ADS states, and I just equate them. And this is basically giving me a way to describe the black hole microstates. So just the general idea is that a black hole, generic BTZ black hole, is a solitonic state in this J algebra viewpoint, this curly J. You may view it as some condensate or solitonic state of the conic spaces. Okay. But let me be a bit more specific. So this I need to only focus on the soft hair sector of this J algebra, which was the algebra associated with the Rindler observer. The reason why I need to exclude n equals 0 here is that any small non-zero energy excitation at the near horizon because of the infinite redshift would correspond to a big or state with big energy or huge energy from the asymptotic observer. So it's better to just only focus on the near horizon soft hairs. So states which are not soft from the near horizon viewpoint should be excluded from this setting. Straight. Okay. These W's are related to the Wilson lines. Yeah. This factor of 2 is because of my convention, but this is supposed to be a primary of weight 1 with this factor of 2. So this is just because of convention. Okay, so we have this algebra of straight J's. I construct the near horizon soft hairs in the same way that I did with the straight J's, but now I'm just excluding this n equal to 0. Okay. Now, just to restate the idea, the black hole, BTZ black hole microstates are among the set of near horizon soft hairs and correspond to states which all have the same delta plus and delta minus. So which was the same mass and angular momentum for the BTZ black hole. Okay. Then it's interesting to give you one more piece of information, and this is due to Baniados some years ago, that any Virasor algebra at a given central charge has a Virasor subalgebra at central charge n being any integer times c. So the map is very simple. Out of these generators, you take those which are an n multiplet of the this Virasor algebra, and this L tildes form another Virasor with bigger central charge. So here I basically showed you two different Virasor algebras, one at central charge 1, the one which was constructed through this W fields or curly J's, and the other one which was constructed from this straight J's and was at Brown-Hano central charge. And they could be related by the same mapping in this way. And I'll use this map to basically, or written in terms of these J operators, to find the black hole microstates. So, please. Okay, and so I try to depict it in this way. I have this space of conic space plus global ADS and their Virasor descendants. I could give two different descriptions. One was in terms of this this algebra with the straight J's, but now this, in this description, the central charge, the Brown-Hano central charge, is coming from this twister. It's just, there is no normal ordering, it's just the classical, if you wish, property. Then I said here, in order to describe this sector, I need to take J naught to be imaginary valued, but instead I could work with these W fields, which are primary fields of weight 1, and this part was an assumption that given this primaries of weight 1, I can always view them as a free field representation for 2D CFT, right? But then they have twisted boundary conditions, twisted periodicity, and if you take this nu to be quantized as 1 over c, there are c number of them, for each and every value of nu. So in this case, actually, I have C different W fields, each corresponding to a state which has a definite mass. Mass is related to this deficit angle nu. Okay? Yes. So, I justified this because it's a free primary of weight 1, and you can just treat it as the momentum conjugate to some field. And basically, the construction I gave here, you can view this either written in terms of this J's or written in terms of this W's. Each W with a given nu is a single field of central charge 1. It's a bosonic field. And then just going back, I have two different descriptions for the same set of states. It's very natural to equate them. And that's what I did here. And the rest is just simple algebra. I had introduced what the BTZ black hole is. From the straight J algebra, it was just expectation value of J between two states was given this. Now I would like to view this as an equation on this Kerley J algebra and this algebra. So basically using this equality and given this definition of BTZ black hole, I'm going to solve what is this P. Very simple. And the answer is the states given written here with the constraint that the sum of these excitations should be C times delta. And the crucial part is this factor of C, which is actually coming with this from this factor of 1 over C here. So, okay. Now, basically, through this Kerley J algebras, I've given you what the explicit presentation of the microstates, and I can do the counting, for example, or whatever you want to do with these states. So just at the 0th order check, I can reproduce the entropy using the standard problem of number of partitions of a given integer into non-negative integers. So for a large n, that's basically how the partition grows. And the log of this is basically giving me the entropy. The first part is the standard Cardy formula, or the area law. Then I have these log pieces. Okay. So so far I've just reproduced the Bekenstein-Hawking. I would like to see whether I can account for the log corrections. So let me just review what some basic facts about the log corrections. So here it becomes important whether we are describing the black hole in canonical or microcanonical descriptions, and because that would affect the coefficient in front of the log term. But the way I parameterize the log corrections is in this way. The entropy is, so this is the area law, and log of the this S naught with the prefactor. And the question is whether we can get the prefactor. This factor of 3/2 with the minus sign is actually coming from assuming that this BTZ black hole has a 2D CFT dual, which is modular invariant. So this is basically the logarithmic corrections to standard Cardy formula. But what I had was not with the factor of 3/2, but was with the factor of 2. So this is basically what I had here. This is this S is the square root of this, so there's a factor of 2. So there seems to be a mismatch, but the mismatch is actually coming from the fact that this equation is written in microcanonical description, whereas this one is written in canonical description. And I'll just show you how to map a canonical description into microcanonical, and it will account for the mismatch of a factor of a half. And to do this, let's recall that as I reviewed earlier, I gave you two different descriptions for the same set of black holes. One was the microcanonical, the other was the canonical map, and I had a map between them. And the map was basically this relation. If I take J naught, which is related to the mass of the BTZ black hole, to be large, namely I take this one to be the dominant part and this part to be the subdominant, I can do the computation and do basically the mapping between the two. So just to remind you again, the entropy in the canonical description is related to the expectation value of this J field on the BTZ state. This was the canonical description, or the Hardy-Ramanujan counting. And the modular invariance was in microcanonical description with a factor of 3/2. And I can use this map and take the expectation value of both sides. And this is the extra piece that I need to compute. For the large J naught limit, I can just do the computation. It's a standard computation. I can take this H field to be a free field in the large J limit, and just it's a standard computation for the expectation value of log of derivative of a free field. And just going through the standard computation, you get the expectation value of this log is exactly minus log of J naught plus some J naught independent fields. So in a sense, if you want, here I need to replace this with log of J naught, and there's a factor of -1/2, which accounts for the mismatch. So if I do the conversion between the canonical and microcanonical ensembles, I'll get the correct logarithmic correction. Okay, so let me summarize. Basically, the horizon fluff proposal states that black hole microstates are subset of states or configurations labeled by the near horizon residual symmetries, while they cannot be distinguished by any asymptotic observer. So that's what the microstate of a black hole should be. And just to go through the proposal for any given black hole, we need to identify what are the asymptotic symmetry algebra, or I have called it asymptotic symmetry just because of I mean, that's the terminology used, but I need not call them asymptotic because they were symplectic symmetries. But in any case, we need to identify the symmetry algebra away from the horizon, at the horizon, and find a map between the two. And then try to solve the equation, which gives the state of any given black hole in the near horizon algebra. So just let me emphasize this last part. So I had this near horizon soft hairs. They were soft. Notion of softness depends on the observer. So these are near soft from the near horizon viewpoint, but they are not soft necessarily from the asymptotic observer. And there is basically a maximum number of excitation that I need to cut off my states, the near horizon soft hairs, not to exceed the mass of a black hole. So that's the picture. And we could show that this works for BTZ black hole. We could also show that if this proposal is going to be true, we need to show that for any Virasoro descendant of a BTZ black hole should have the same entropy. And we actually have shown this is true. Namely, the set of microstates for a descendant of a BTZ black hole is not exactly the same as the microstates of BTZ, but their number is the same. So the entropy in the end is independent of the Virasoro excitation. And here I introduce this, if you want to call it in a strong sense, a duality between these W states or curly J's and these straight J's. It's desirable to understand this better. So obviously, if I have a theory which has this Virasoro generators of this form or this form, this equality means that the partition functions of the two theories should be equal already. So, but it's better, it's interesting to check it in some specific examples, whether this duality comes true or not. And then it's of course interesting to extend it beyond BTZ and three-dimensional black holes, in particular generic Kerr black hole. We have shown that it works for extremal Kerr, but we think that it should also work for generic Kerr black hole. So, thank you.
So is it correct to say that in your interpretation, the microstates of a given classical solution is just given by another set of classical solutions?
It's not classical solutions, because we had a complicated multi-particle state. I don't know whether individual particles may have some geometric description, but not this generic multi-particle state that I showed. So there was a step of this semi-classical quantization. I went from fields or functions which were appearing in the metric to operators. So I can, for each microstate, I can try to give you something which looks is close to a classical geometric description of the microstate, but that's not a precise statement.
Because the counting you're doing is like these microstates are just given by acting with the JNs on some near horizon metric, right?
This curly JNs, yes. Yes.
So that's a classical geometry, just the finite diffeomorphism acting on near horizon geometry.
But again, here, just let me show you the. There's a generic product of all of this. Individually, I know what's the microstate. What's the geometry, but not this complicated product.
Why not? Why not?
So I can give you a geometry which corresponds to expectation value of this on some background state, but that's not the microstate itself. This is something which.
Okay, thanks.
That's the expectation value of this operator, which would correspond to some close-by geometry. Okay. So for four-dimensional black holes, again, let's, for example, take the generic Kerr, to be specific. The horizon, the bifurcation surface, is topologically two-sphere there. Then I need to have two sets of this J, actually 4 sets of these J's, two left, two right. And out of this I can construct a BMS algebra, which would replace the Virasoro algebra here. And then do the same, but everything is now given in terms of this U1 J algebras, if you want, at the end. And I can construct the Hilbert space of those. It's a bit more complicated. It's like doubling this. And there.
Yeah, so you mentioned conical singularities, I guess with deficit angles, or do we have also room for excesses? I mean, angles greater than 2 pi?
Okay, that's a very good question. Here, actually, I restricted myself to, I didn't emphasize it, but since to unitary representations of this algebra. Unitary representations means that there's a limit on this nu, which should not exceed 1. So to be more specific, I'm just restricting myself to states which are normalizable and unitary on a single cover of ADS3. For the excesses, I need to go to multiple covers of ADS3, which are not unitary representations of this Virasor algebra. So that's a very interesting question to explore. But here I have just taken to work with unitary representations. Mm-hmm.